In this video, we will discuss about the interactions of time-varying charges. Time-varying charges will produce a time-varying electric field and also a time-varying magnetic field. To explain the interactions of time-varying charges, we need to know the Faraday's law of electromagnetic induction. Faraday's law states that when the magnetic flux linking a circuit changes, an electromotive force is induced in the circuit that is proportional to the rate of the flux linkage. The mathematical form of Faraday's law is shown on this slide. It is said that VEMF is equal to negative d lambda over dt, where VEMF is the electromotive force and lambda is the flux linkage, and d lambda over dt is the rate of flux linkage, and lambda can be written as n times phi, where n is the number of turns of the coil and phi is the flux, and phi can be written as flux density times the surface area, or the surface integration of P dot ds. Therefore, VEMF equal to, um, we put the derivative inside the integration and change it to partial derivative. So it becomes partial B over partial T dot ds, and whole thing will be taken off a surface integration. We also use negative sign for Faraday's law. This negative sign comes from Lenz's law. The meaning of this negative sign is the induced EMF direction will be opposite to the flux change direction. Now, if we apply Kirchhoff's law in electric circuit, you know the source voltage is equal to the voltage drop in the electrical components. So you can write the VEMF is the source voltage or battery voltage that is equal to the voltage drops in the circuit element, and circuit if the circuit is closed. So you can write it like closed integral line integral of E dot dl. So if we combine this Kirchhoff's law with Faraday's law, we can write it like integration of E dot dl is equal to surface integration of partial B over partial T dot ds of negative. Then E dot dl, equating this, you can come up with the integral form of Maxwell's equation. You can see the integral form of Maxwell's equation is the circulation of E field over a closed path is equal to negative the surface integration of partial B over partial T dot ds, and the respective point form of Maxwell's equation is curl of E is equal to negative partial B over partial T. And here you can see how you can see that if you change the magnetic field, like if the magnetic field from left to right, if you change it to left to right, the current will be right to left, the induced current will be right to left, and polarity got positive here. Now if you move to negative north to south, or right to left, current direction will be opposite and the induced voltage will be opposite too. And you can see in this GIF that when you move the magnet inside the coil, there will be a voltage induced in the coil, and this voltage will turn on the light. So you can see the flashing light here. When the flux change is maximum, the light intensity will be higher. When the flux density is low, the light intensity will be less. So in this slide, we will learn about a new type of current that is called displacement current. We already learned about conduction current, that's the ohmic current. So if there is a conductor, the current will flow inside the conductor, that's called the conduction current, and we can use Ohm's law for solving or finding the conduction current. But in addition to this conduction current, there can be another type of current that is called displacement current. To understand the displacement current, we need to know the continuity equation. From the continuous flow of current, the current is equal to negative the rate of change of charge. So, or charge can be written as a charge density over the volume charge density over the volume, and if you change the derivative to partial derivative, you can put the integration at the back, and the current also can be written as current density over the surface integration. So, and that is equal to d rho over dt. So if you equate these two equations, you will get the divergence of J equal to negative dw over dt. So we come up with this equation by from the definition of current by using continuity law. Now if we consider the Ampere's law that we have obtained before, we know the curl of A is equal to J. So curl of A is equal to J. If I take divergence on the both sides, then according to mathematics, divergence of curl of A will be 0. That gives us divergence of J equal to 0 too. But here we got divergence of J equal to 0 from Ampere's law. But from continuity equation, we say divergence of J equal to negative d rho over delta t. So now we found that these two relations are not same. So the Ampere's law and the continuity equation got a different point here, stand in a different point. So how we can solve this problem? So to resolve these problems, we have to define a new type of current in the Ampere's law. So let us define a current ZD in the Ampere's law, and we modify the Ampere's law equation that curl of A is equal to J plus ZD, and then we write the divergence of J, then will be divergence of negative divergence of ZD is equal to negative d rho over dd. And from this we can also write ZD is equal to the time rate of charge density. And finally we can come up with a new or modified Ampere's law, that is curl of A is equal to J plus ZD, where this current density J is the conduction current density, and this divergence d over partial d over dt is the rate of change of flux, that is called the displacement current density. Actually, if there is no conductor like capacitor, there is no conducting way, there is some free space or dielectric space between the conducting plates, we can see a current, charging or discharging current inside for the capacitor. This type of current is produced because of the flux. So the capacitor plate will be charged up, and a static flux or a tempering flux will set between the plates, and this flux sense is contribute to a current. That current is called the displacement current. So however, we need to modify the Ampere's law for time varying case, For time varying case, the Ampere's law has two terms. One is the conduction current density term, and another is the displacement current density term. Now, for integration, if we use the integral form of Ampere's law, then we have to take the line integration of H, the circulation of H in the, around the closed path is equal to the current, conduction current, plus the surface integration of rate of change of flux times the surface. So if you write the Maxwell's equation in the integral form and the point form for time varying fields, you can find this first equation for the Faradays law comes from the Faradays law, and the second equations that comes from the Ampere's law with the displacement current term, and the third equation, so that is the very same to the static equation, so that surface integration of d dot ds is equal to q, the charge enclosed. This is comes from the Gauss's law. And the fourth equation is surface integration of b dot ds is equal to 0, that is called magnetic isolated magnetic flux law. And in the point form, we can write that rotation of E is equal to negative dB over dt, partial B over partial t, and curl of H is equal to the conduction current density J plus the displacement current density partial D over partial t. And divergence of D is equal to rho B, that's the point form of Gauss's law, and divergence of B equal to 0. So these four equations are called the Maxwell's equation. This for time varying field. These four equations are the integral form, and the other four equations for the point form. You need to memorize this equation because we will be using this equation for almost every day in this course, and in the test you will be asking to write down these equations for different mediums, for different materials, and for free space and so on. So if you don't memorize this equation, that will be a very problem for understanding this course. So I would like to recommend everyone to memorize these 8 equations, 4 integral form equation and 4 point form equations. In addition to these 4 equations, we already have learned some other equations. One is the electric field equations, and another one is the flux density, and then we have learned about these equations are for static field. So we are going to learn their respective time varying expressions. So we already have learned about the Maxwell's equation in time varying case, and this equation and the other equations need to be modified for time varying field. Especially we have to modify the electric field equation for time varying case, and also we need to modify the magnetic field equation for time varying case.